In section 7, we're turning to analysis of these binary outcomes for dataset 2, suicidal ideation and substance abuse. On slide 59, I just remind you of the notation that we have for these different models that was introduced in part 1 of this Webtalk number 4. So you have on the one hand classic dynamic models where y is regressed on y at the previous time point. In this case, we work with y stars. And RI models with dynamic models for the residuals, y hat regressed on y hat at the previous time point. So in the classic category, we have the autoregressive model, AR1, AR2, which is used in one of the two parts, one of the two processes in cross-leg panel model in the classic approach. And then you have the ARMA model, AR, moving average, which is dynamic as well. That one can only be estimated by WSMV. So we're going to focus here on base estimation, but there are a couple of models that cannot yet be estimated by base, so we will switch to WSMV for those models. And then we have these two models which have an RI component, but it's still a dynamic model in the classic sense, that is regressions of y stars on y stars. So we have the RI-ARI and the RI-ARMA version of that. And again, that one can only be estimated by WSMV. So for ARMA models, we have to rely on WSMV. And then the RI model with dynamic models for the residuals, so RI-AR, for instance, RI-AR1, which is used in RI-CLPM, where the AR is specified the residual, the within level latent variable centered part. And the new RI-ARMA model, where an ARMA model is specified for the residual. So we add a moving average component to the RI-AR model. And again, that can only be estimated by WSMV. Then we can do this average Tetrachoric correlation plot that we used also for the stress variable, the continuous variable. So here you have then time distance in years on the x-axis. And we have 8 time points, so the time distance goes from 1 to 7. It's a little bit different x-axis than in the population correlation plots I looked at with you earlier. So we have it for the suicidal ideation outcome and for the substance abuse outcome. So we see then that both plots suggest an asymptote that is larger than 0. Suicide comes down lower, but it ends up a little bit above 0.2. Substance is a little bit higher up. And we note then that here at the endpoint with the time distance 7, there's only one sample correlation contributing to this average, whereas for other time distances we have several time points. So this is a correlation, this is a plot point that is the least reliable. And it also is the least reliable in the sense that it relies on correlation between 1 and 8, time point 1 and 8, which typically has the lowest coverage. I think for these data the coverage was about 0.70 for that correlation, where it's over 0.8 for most other correlations. So the random intercept variance is suggested to be a little bit lower than what we saw for the stress outcome in the combined data, where it was ending up about 0.5 here. And the plot suggests then, comparing the two curves, a higher AR and a higher random intercept variance for substance abuse than for suicidal ideation. Now, turning to the analysis of suicidal ideation here then. Again, we're going to focus on Bayesian analysis with some added WSMV runs. And I should mention that output for all of these models here on this slide and the next are posted on the website of the talk. Now we're going to pay attention to a model fit of two kinds, both the chi-square fit, or the posterior predictive probability fit using Bayes terms, but also the fit to the frequency data and the bivariate tables for pairs of variables. So the fit of the model to the data, not only the fit of the correlational structure. And we're going to note then that the most frequent response pattern is the one that has zeros throughout all 8 time points. So there are 155 who are in that category, 155 of the 737. So a sizable number of people. And we're going to then notice that we have 112 bivariate cells, which is obtained as 4 cells per pair and 28 pairs. 8 times 8 minus 1 divided by 2. 5%, if you're going to have the 5% rough criterion for acceptable number of misfitting cells, that would be 6 such cells. And I'm going to actually take the liberty to have a subjective assessment of fit in terms of 4 categories: good fit, okay fit, marginal fit, and poor fit. So I'm going to add that comment in the last column here for the outcomes, for the models rather. So we're going to have the model number of parameters, the Bayesian PPP, or the WSMV chi-square, and then we're going to look at the number of significant residuals for the response patterns and for the bivariate tables. Model number one is then the simple AR1 model, which has a PPP of 0.133 with significant residuals, 2 significant residuals, one of them being for the most frequent pattern. So this is not a happy outcome. You want to be able to fit the most frequent pattern without it being significantly misfitting. 22 bivariate significant residuals, which is far more than the 6 that we mentioned up here. So I'm calling that a poor fitting model. So you have to go to lag 2 models here, for which PPP increases and the frequency fit is perfect and the bivariate fit is very good. So I call that an okay fit, and perhaps I should even call it a good fit. Now I do that model also using WSMV. That's when you get the asterisk denoting WSMV. And then you get the 15 degrees of freedom, chi-square of 38, and a p-value of 0.001, so you get something greater than 0 at least. And in terms of frequency fit, it's perfect, and bivariate cell fit is also very good. So an AR2 model seems to be reasonable, and certainly much better than the AR1 model in terms of fit, and in terms of also the jump in PPP. Turning to the ARMA model then, AR1, A1, so 1, can only be fit by WSMV. The same number of parameters, you get a much better fit. 15 with 17 instead of 15 with 38 here. So the p-value jumps up and we have a good fit. Now adding an RI component, AR1, that's adding 1 parameter to the AR1 model up here, namely the random intercept. You increase the chi-square fit. Well, we can't see it. Yeah, we can see it in the PPP value going from 0.133 up to 0.474. And in chi-square terms, we get a fairly good chi-square fit here, very good, and good frequency fit as well. Now for the ARMA model, in the case of a random intercept, we get 23 degrees of freedom, 23 parameters, and 13 degrees of freedom with chi-square equals 11. So I would call that an overfitted model. It has more parameters than you really need to have. Okay, on the next slide then you get to the models that make a separation between the random intercept and the dynamic process. RI-ARI seemed to fit quite well in terms of base, high PPP, and good residual fit. The WSMV version is not too bad either, getting close to a p-value of 0.01 at least. But you can improve it further if you add a lag2 model where the WSMV p-value increases, and certainly the chi-square fit seems to be quite good here. Turning then to the new RI-ARI model, same number of parameters, chi-square improves drastically, but you get a negative variance for the random intercept. And this is something you want to keep an eye on. And I would call this model, again, over-parameterized, again in the sense of having the chi-square value being even lower than the number of degrees of freedom, so the p-value gets very high. Now you can fix this residual variance at 0, and you get a good, well-fitting model, but that's the same model as number 3, same model as on the previous slide, ARMA 11, because that doesn't have the random intercept. So you have really not gotten any advantage out of using the RI-ARMA model here. But we can see then what a good improvement model number 7, for instance, has. Chi-square with 14 degrees of freedom is 25. If you go back to the AR2 model, 15 with 38 versus 14 with 25, p-value jumps up to 0.03. So the adding the random intercept, that is the one parameter, going from 21 parameters here on slide 61 to one more parameter, improves chi-square quite a lot. So here I would say you could go either with the RI-ARI or the RI-ARI2 model. On slide 63, you have the results for the RI-ARI model for suicidal ideation. And we note then first that we have a substantial random intercept variance where you have the point estimate met 0.756 and a standard error, which is the same thing as the standard deviation in the Bayesian posterior distribution of 0.102. And the ratio is quite large here between the two. So it seems to be a well-defined random intercept variance. Let me look at the standardized estimates for the random intercept loadings, which then can give you the correlations, say, between the first and the last time point here due to the random intercept, is the standardized loadings, product of them for the first and the last time point. It's about 0.38, with a total estimated correlation of 0.383. So you get a little bit of contribution, but very little from the autocorrelation. So you have a value of 0.38 here approximately, and R squared for the last time point, it's a square of the last standardized loading, 0.34. So you can compare that with the plot that we had for suicidal ideation. So we had 38 and 34 estimated values here at last time points. It's a little higher than the observed correlation there. It may be a slight misfit. Maybe we need to go to RI-ARI2, or it may be that that observed correlation is poorly determined. Looking at the right column, then we see the autoregressive coefficient standardized, and we find then that the first time point, or the first two time points, you have a negative value. It's insignificant. And the second time point is also insignificant. And only then between autoregressive coefficient between time point 4 and 3 do you get the expected positive value, which is 0.3, and it's significant. And then it tends to be a little bit higher for the later time points, and also significant values. So in this case, the autoregressive coefficients are allowed to vary across time, unlike the those theoretical plots, correlation plots that we showed earlier, where we held AR1 equal across time. Now turning to substance abuse then, on the next two slides. Here the frequency of the most frequent response pattern is 201. And we see that the first model does not fit that well. You have a misfit, a significant residual for that most frequent response pattern. And 14 bivariate, which should be less than 6, we agree with. Poor fit for that, and you need to go to 2 time points, lag 2 model, where you have a much better PPP, and you get an acceptable chi-square fit here, also in terms of the response patterns. Not any important standardized significant residuals. The ARMA model fits well, but it seems to be hugely overparameterized. And then when you add the random intercept, you get a better fit, but actually not as good as you did with the AR2 model here. If you turn to the ARMA model, you also have an overparameterized model. So going to the next slide, 65, the standard RI-AR1 model, how does that fare? Well, you have a misfit for the most frequent response pattern, which we agreed, if you go back, there was a slide on the previous slide was 201. So I would call that a marginal fit. That's poorly fitting, but the bivariate fit is reasonable, so I call it a marginal fit. The chi-square for that is, however, poor, so I call that a poor fitting model. Adding lag 2, you get a chi-square that's reasonable, and the RI-AR2 model seems to be acceptable. We do have this blemish here on the fit by having the most frequent pattern misfitting, but I give it a double asterisk here, saying that the z-score is 2.01, so just marginally above the 1.96 value. The RI-ARMA model is reasonable, and in this case we do not have any problem with negative random intercept variances. So that is also a possible model for these data.